Hello, ladies and gentlemen. Welcome to Skill 29, which is linear approximation. As physicists like to say, approximate everything as linear mathematicians. The first order was only the beginning. So one thing that's beautiful about this skill, actually, is that you can turn calculus into an algebra 1 problem into a 6th grade math problem, just by the power of using derivatives. So I'm going to kind of show you what I mean. So back in the olden days, before the days of calculators, you could actually estimate numbers and values of like curvature functions by, instead of actually looking at the curvy function, thinking about its derivative or instantaneous slope. So if I wanted to find like the y value of this point, maybe instead of actually using like the curve, I could actually use like the tangent line and it would be almost the same exact thing. So this is why it's called a linear approximation. So I think that this picture is helpful to include in your notes, just so you can have a good visual of the concept. All right, so let's actually get you reading a question here. So I'm just going to kind of immediately give you the question, just so we can kind of see what is provided and what it looks like. And then I'm going to give you a checklist, and then we're going to solve this example. So it says, let f be a differentiable function such that f of -5 equals 9. So this is the first piece of information provided on the linear approximation level 1s. So I have f of -5 equals to -9. So this means that the function goes through point -5, -9. And I'm actually just going to call this x1, y1, kind of like in the old days of distance formula or slope formula. And you will see why in a second. Okay. The next thing here is that they give you f prime of -5 equals to -6. So this means that the slope at -5 equals to -6. So we could actually say that m equals to -6. So I got m and I got x1 and y1. So I have a point and a slope. Guess where we are going? We're going back in time to Algebra 1, where we are actually going to be looking at the point slope form of an equation of a line. And what I am shooting for is y. So it's asking us, what is the linear approximation of f of -4.95? So what this is asking us essentially is, what is the y value at -4.95? So actually, if I want to do that, I could actually just move the y1 to the other side. And this would actually be like your x. So I could say like the x that is not like the x1, but I could just say that x is -4.95. So I have all the pieces of information that I need to actually come up with that y value. So we're actually going to solve this very soon. So I'm just going to give you a checklist first of what you need to do and then we're going to kind of just go down the checklist and do it. All right, so what are you given? So you're going to be given an XY coordinate that can be determined from the function. You're going to be given information about its derivative. Now, I'm going to give you just one level 2 as well. And the difference on that is that on a level 2, this will just be on the practice and not on the assessments. But on level 2, I'm going to give you kind of like a derivative equation. And you're actually just going to have to find the instantaneous slope. And you're just going to have to work a little bit more to find what you need. So you always want to make sure that you are using your point slope form equation. You want to convert into getting that y by itself. And you want to plug in your xy coordinate that you're given and also the x value in question as well. So let's do this. So what I'm going to do here, when I read this, I like to kind of circle. It looks kind of wordy, so I'm just going to like translate this into the from like the pre-calc calculus speak into more, you know, algebra 1 style speak. So what this is telling us is that the function goes through the point -5, -9. So this is our x1 and y1. So I'm just going to kind of circle that. This tells us that the slope at -5 is -6. So what I'm going to do here is I'm going to put into point slope form. So I'm going to write y minus y1 equals to m times x minus x1. And it's asking me for the approximation at f of -4.95. So the x that is not the x1 but just x will be -4.95. So I have all the key pieces of information that I need. So what I'm going to actually do here is I'm going to plug in everything that I know. So I don't know y, but what I do know is y1. So that's going to be -9. My slope is -6. And I have a -4.95 for my x. And then my x1, hold on, I just added one thing in there. Get this fixed. -4.95 minus -5. So I have y plus 9 equals to -6 times, and remember, this is kind of like your order of operations here. So I have -4.95 plus 5. And I'm just going to move the 9 over. So I got -6 times -4.95 plus 5 plus 9. Or minus 9, I should say. I moved it over to the other side. And I'm just going to add -4.95 plus 5. That's 0.05 minus 9. So this is going to be -0.3 minus 9, or -9.3. So on the linear approximation level 1s, you know, we're kind of going to be the level of your mastery. It will be this level of question, and you will end actually at a number. So what this means is that f of negative 4.95 is not negative 9.3, but approximately negative 9.3. So it's not the exact y value, but it's pretty darn close. So why do we care about linear approximations? How was this used? So this is a cool exercise that I did a few years ago with my calculus class. Do you ever wonder how calculator, kind of works? And how, we were able to come up with square roots of certain types of numbers? Well, it turns out that some of the thinking actually does come from like linear approximations. So you can actually come up with not an exact value of the square root, but something that's pretty close. So here's something that we know from like the good old days of like middle school. We know that the square root of 64 is equal to 8. So I'm going to say, let's say we want to find the square root of 65. So we have a function that is the square root of x. And we know that one, like our coordinate here, we actually know that the square root function goes through 8. Actually, 1 minute. We know that it goes through 64, comma 8. Because f of 64 equals to the square root of 64, which is just equal to 8. Now let's say that I want to find my slope. I'm just going to call this my mcalc. So one thing that I can actually do is if I know that f of x is equal to square root of x, which is x to the 1/2, I can figure out what f prime of x is equal to. So that would be 1/2 x to the negative 1/2. Or I could just put this in the denominator. So the 2's in the denominator. The x moves into the denominator. So this is 1/2 times square root of x. And if I want to find f prime of 64, I could actually plug in 64. So this would be 1/2 times 8, which is 1/16. That's equal to our m. All right, and then now, third thing I'm going to do is I'm going to do point slope. And we also know that I'm looking at the square root of 65. So x is equal to 65. And then I have x1 and y1 are 64 and 8. So I'm just going to kind of play inventory here. So x1 was 64. Y1 was 8. M is 1/16. And we can say that x is 65. So I'm going to write y minus y1 equals to m times x minus x1. And I'm just going to plug in everything that I know. So my y1 is 8. My m is 1/16. And then my x is 65 minus 64. And I'm just going to clean things up a little bit. So I got 1/16 times 1. So I could actually then add 8 on both sides. And I could say that the square root of 65 is approximately 8 1/16. Or if I wanted to know what that is in decimal, if I have 1/16 in my calculator, that's going to be about 8 point, well, actually, it's going to be 8.0625. So I'd like you to kind of hold that in the back of your mind. And the actual square root of 65 on my calculator wait for it. So the approximation that we got was 8.0625. So the actual square root of 65 is 8.0625, and it just kind of like repeats with like kind of random decimals after that. But the bottom line here is that we got to 8.062. So we're actually within a few 10,000ths of the actual answer, just with the knowledge of a power rule derivative, maybe a mid-level power rule derivative, knowing that the square root of 64 is 8, and knowing point slope form from algebra 1. And that's really, really cool. So I think that is really neat, actually, and how derivatives can actually really make people's lives easier.